The next topic of our discussion is your strain tensor. We already see that what is the stress tensor. A stress tensor is a matrix form which is used to represent the state of a stress at a point under tri-axial loading, or you can say under any loading. So if you want to know what is the state of stress at a point on the three mutually perpendicular planes passing through that point is denoted with the help of your stress tensor. The strain tensor is similar to the stress tensor, which is also represent the state of strain at a point, that is the number of strains acting on three mutually perpendicular planes passing through it, right? If any three mutually perpendicular planes are passing through a point, then the number of strains acting on that three perpendicular planes because of some loading is known as your strain tensor, right? That is similar to the stress tensor. In stress tensor we have normal stress sigma and we have shear stress tau. So to show the normal strain and shear strain on your strain tensor, just you have to replace the sigma with the normal strain, that is epsilon, and shear stress with the shear strain gamma by 2, right? You just need to replace the normal stress with normal strain and shear stress with shear strain divided by 2. So if I can say that we know what is the stress tensor, if I write again, that is the stress tensor in three-dimensional thing. So it will be sigma x, tau xy, tau xz, this is tau yx, this is sigma y, this is tau yz, this is tau zx, tau zy, this is sigma z. This is the stress tensor in 3D. Now I want to know what is the strain tensor. Then the strain tensor in three-dimensional or tri-axial loading will be like this. Just replace the sigma with epsilon. So I can write this is epsilon x and replace the tau with gamma by 2. So this is gamma xy by 2. This is gamma xz by 2. Simple, you just need to replace the things. This is tau yx, so this is gamma yx by 2. This is epsilon y. This is gamma yz by 2. This is gamma zx by 2. Gamma zy by 2. And epsilon z. So this is the strain tensor in case of three-dimensional or tri-axial loading. This is your strain tensor in case of your tri-axial loading, and as your complementary shear stresses are equal, and so this is the same applicable for complementary shear strains. So we can say that complementary shear strains are of equal magnitude. Same thing applicable for the strains also, are of equal magnitude and of opposite direction, right? Are of equal magnitude, right? So if you see that there is no direction of strain, okay, I can remove this. So complementary shear strains are of equal magnitude. So I can replace it like this. So gamma xy and gamma yx will be equal. Gamma xz and gamma zx will be equal. And gamma yz and gamma zy will be equal. So you can say that your strain tensor is also symmetric about its principal diagonal. This is the principal diagonal. So The strain tensor is also symmetrical about its principal diagonal, just like in case of your stress tensor, which is also symmetric about its principal diagonal. So if I want to know what is the biaxial state of strain, biaxial state of strain, because in our syllabus we have to deal with biaxial state only. Biaxial state of strain means, let us suppose the z direction dimension is negligible, so I can write your epsilon z equal to 0, gamma zx and gamma zy is also equal to 0. There is no strain in the z phase, so if gamma zx is 0, then gamma xz is also 0, and if gamma zy is 0, then gamma yz will also be 0. So the state of strain or the strain tensor in case of biaxial state of stress will be epsilon x gamma xy by 2. Here also gamma xy by 2, because gamma yx and gamma xy are equal, so and this is epsilon y. So this is your state of strain or strain tensor in case of two-dimensional body, right? In case of two-dimensional or in case of your biaxial state of stress, right? So this is the strain tensor. Now let us go to the topic that what do we mean by strain, right? What is the meaning of strain? We can say that the strain is your change of dimension, right? We already see in strength of material, whenever you applied an external load to a body, the body is a deformable body, so its dimension will try to change, right? And this change in dimensional or change in this dimension, the dimension would be anything, right? Divided by original dimension is your strain, right? So for a strain, we know that the body must be a deformable body, because in case of rigid bodies the strain will be 0, and if there is a strain developed inside a body, so because of this strain, stress will develop. So you know that strain is the cause of stress, that because first thing happened is the strain deformation, that deformation is resisted, and because this deformation is resisted, one internal resisting force is developed, that is equal to the stress. So we can say a member or a body is said to be strained whenever the relative positions of the particle, the important thing is relative, not position of the particle. This is the initial position of the particle, this body will move to this position, so the position of particles will be changing. We are not concerned about the position of the particles, we are concerned about the position with respect to each other, relative to each other. If suppose these are the two molecules, if there is a distance of 1 mm between them, so if I move it from this point to this point, the relative change of position will be 0. So we are not concerned about the change of position, we are concerned about the relative change with respect to each other. So we say a body is said to be strained whenever the relative positions of the particle is changed in presence of loads acting on the body, right? So we can say first is you applied a load, body deformed, strain will be there, that strain is resisted. To resist it, one internal resisting force is developed, and that internal resisting force per unit, so the stress is developed. So this is a cycle that, or this is the process, load, then strain, then stress. So there are two types of strains we have in strength of material. One is the normal strain. Normal strain is because of the normal load, and one is your shear strain, that is because of shear load, right? Normal strain is because of normal stress or the normal load. Normal load is of two types, we know, axial load and bending moment. and shear strain is because of some shear load, and shear load is also of two types. One is transverse shear load and one is twisting moment, right? So the normal strain is of three types. For the classification of normal strain is longitudinal strain, volumetric strain and lateral strain. These are the three further classification of strains or normal strain: longitudinal, volumetric and lateral, and these three will further classified into tensile strain and compressive strain, right? We know this. So let us see what do we mean by the normal strain. So we can say that your normal strain is, if you say that normal strain is your change in dimension upon original dimension. Change in dimension upon original dimension. And we know that because of your normal strain, if I apply a normal load on this, its length will increase, its diameter will decrease. So the dimension of this body or the dimension of this cross section will change, right? Because of the normal load. So you can say that this will be helpful for you in your numerical part, that because of a normal strain, your dimension of cross section will change. The dimension of cross section will change because of normal load, and that change in dimension upon original dimension will give you a normal strain. Now which dimension? Suppose this is a body, this is the length of the body, or if I draw here, suppose this is a member, L is the length of the member, or you can say this is original length, that is before loading, and D is the diameter of the member, that is your original diameter before loading. So this is the length and this is the diameter. If I applied a axial load on this, axial is a normal load, then its length will increase, its diameter will decrease, so that volume remains constant. We know this. So we can say that suppose its length will increase and its diameter will decrease. So the final, after loading, this rod will be like this. Its length will increase and its diameter will decrease. The rod will be like this after loading. The rod will be like this. So we can say that LF is the final length of the body, final length of rod you can say, and DF is the final diameter or after loading diameter of rod, right? Final length of the rod and final diameter of the load. So we can say that this is your DF and this is your LF, final length. So we have the normal strain as the change in dimension upon original dimension. Just take care here, change in dimension upon original dimension, but because of the load, that is a normal load, two dimensions are changing. Length is increasing and diameter is decreasing, right? Two dimensions are changing here, length is increased and diameter is decreased. So we have two strains from here. One is the change in length upon original length, and the another is change in diameter upon original diameter. We have two strains in this, and both of the strains are normal strains, right? Both of the strains are normal strains because they are because of this your normal loading. So we have two strains. One is your change in length upon original length. The length is increased, so this is a tensile strain. And another strain is change in diameter upon original diameter. The diameter is decreasing, so it is a compressive strain. Both of them are normal. So the normal strains are of two types. One is the longitudinal strain and one is the lateral strain. The longitudinal strain gives us the strain in the direction of applied load. Please take care here. The strain which is in the direction of applied of load, that direction is known as, that strain is known as longitudinal strain. In this case, the load is applied along the length. The load is applied along the length. So I can say that in this case, the longitudinal strain is equal to change in length upon original length. Right? Change in length upon original length. That is the longitudinal strain in this case. This longitudinal strain in this case is of tensile, right, in case of tensile nature, and this is applicable when the load is acting along length, right. Load is acting along length of the rod. So longitudinal strain will give us the strain, or will give us the strain in the direction of applied load. Suppose if instead of this load P in the direction of length, I applied a load P in the direction of diameter, right. If this is the case, this is the length, this is diameter. Suppose this is a rod. Instead of applying a tensile load in this case, I am applying a tensile load in this direction along the diameter, right. I am applying a tensile load along the diameter. So in that case, the diameter is increasing. So if diameter is increasing, the length will decrease to maintain the constant volume. So in this case, the change in diameter upon original diameter is longitudinal strain. Right. So don't confuse. In this case, the change in diameter will be the longitudinal strain, but in this case, the change in length is the longitudinal strain. Right. And in this, if the load is tensile, so it is a tensile strain. If you applied a compressive load along the length, then it will be of compressive nature. That is the definition of longitudinal strain, which is also a normal strain. Now longitudinal strain is also a normal strain, but the normal strain is change in dimension upon original dimension, but longitudinal strain is change in dimension upon original dimension in the direction of applied load. In which direction the load is applied, in that direction the strain is the longitudinal strain. Let us discuss what is the lateral strain. We already see that there are two types of strain, normal and shear. And normal strain is your change in dimension upon original dimension. And normal strain is of two types, longitudinal strain and lateral strain. And we know that the longitudinal strain will give us the change in dimension upon original dimension in the direction of applied load, right. In which direction you applied a load, in that direction the change in dimension upon original dimension will be given by the longitudinal strain. So lateral strain will give us the strain in the direction which is perpendicular to the applied load, right. We can see that, let us suppose this is a bar, the initial length is L0 before loading, and the initial diameter of this rod is D0 before loading, right. When I apply a tensile load on this, or an axial tensile load over this, that is P, so because of this load the length of this rod will increase, and I am saying that the final length is LF. Because the length is increasing, so diameter will decrease, because to maintain the constant volume, so the final diameter is DF, right. And we are supposing that this is your x-axis, this is y-axis, and this is your z-axis, right. X-axis, y-axis and z-axis. Now we can say that lateral, in this case we know that the longitudinal strain is epsilon, which is equal to your final length minus initial length upon initial length. This is the change in dimension upon original dimension, and this will be of tensile nature, right? Because it is a tensile load and this LF is more than L0, so this value is positive, so it will give us a tensile load. And this strain is in X direction. In X direction, the length is in X direction, so this is epsilon X, right? This is your epsilon X. So we can say that the longitudinal strain is the strain which is given in the direction of load, direction of the applied load, and lateral strain gives us the strain in the direction which is perpendicular to the applied load. This is the direction of load, so perpendicular, that is y-axis or z-axis, the strain in y-axis and z-axis will be the lateral strain, right? So we can say from here that the lateral strain is equal to, if I can write epsilon, that is lateral, which is equal to your final diameter minus initial diameter upon initial diameter. This is the change of diameter upon original diameter, and the final diameter is less than initial diameter, so this is of compressive nature. This is of compressive nature, and we can say that this is your epsilon y in the y direction. This is epsilon y, and epsilon z in the z direction is also equal to your df minus d naught upon d naught, right? In the z direction also the diameter is d, so we can say df minus d naught upon d naught. This is your longitudinal and lateral strain, the concept of longitudinal and lateral. If I can see that if instead of load P in x direction, if I applied a load in y direction, then the change in diameter upon original diameter will give longitudinal strain, and in that case the change in length upon original length will give you your lateral strain. So in the direction of applied load, we can say that the strain is longitudinal, and the direction perpendicular to the applied load will give you the lateral strain. So if I can say that every longitudinal strain, any longitudinal strain is associated with two lateral strain, right? If I apply a load in x direction, then in x direction strain is longitudinal, and because of this longitudinal strain, two lateral strain also came, because to maintain the constant volume, that is we know, right? So the two lateral strains on the perpendicular planes to the plane of this direction of load will give you the lateral strain. So every longitudinal strain will be associated with two lateral strain of opposite nature, right? The nature will be opposite. If longitudinal strain is your tensile strain, then lateral strain will be of compressive nature. So if I can say that if there is your tri-axial loading case, right? If in a tri-axial loading case, I can say that the load is in all the three axes, x-axis, y-axis and z-axis. So we can say that if I draw the diagram here, let us say in this case, suppose this is a cubic body is there. We have three axes, x-axis, y-axis and z-axis, right? Suppose this is your x, this is your y and this is your z, right? This is your z. So in x-axis, let us say we have a tensile load, that is px. In y direction we have a load py, and in z axis we have an axial load, that is pz. So we can say that because of px, in the x direction we have longitudinal strain, and in the y and z direction we have lateral strain. because of Py, on this y-axis or on this y face we have longitudinal, and on x and z face we have lateral. Because of this Pz, we have a longitudinal strain on this z face and lateral strain on the plane perpendicular, that is y and x. So we can say that under any triaxial loading, this triaxial loading case, the body undergoes 9 strains, right? 9 strains. Because in this, because of x, we have epsilon x, that is the longitudinal, epsilon y and epsilon z is the lateral. Now if I write here, we will show with the different markers. If px strain because of px I am showing with black color, so I can say that because of px, this is your longitudinal strain, and on y face we have lateral strain, and on z face we have lateral strain, right? If because of Py, I denote the strain with blue color marker. So because of Py, we have epsilon y, that is longitudinal, epsilon x, that is lateral, and epsilon z, that is also lateral. Because of Pz, we have epsilon z, that is longitudinal, in this direction longitudinal, epsilon x, that is lateral, and epsilon y, that is also lateral, right? So because of this 3 axial loading, we have these 9 stresses. Out of these 9 stresses, 3 are longitudinal, this epsilon x, this epsilon y, and this epsilon z, longitudinal, and the 6 are your lateral strains. And in each direction, that is in x and y and z, we have one longitudinal and one lateral. You can see this is the stress strain in your x direction. In x direction we have one longitudinal and 2 lateral. In y direction we have one longitudinal, 2 lateral. In z direction we have one longitudinal, 2 lateral, right? So in each and every case we have one longitudinal and 2 lateral strain on each direction. And every longitudinal strain will be associated with 2 lateral strains of opposite nature. And we know from our earlier discussions that the Poisson ratio mu will be the value of your Poisson's ratio, that is mu will be you can say lateral strain upon longitudinal strain, right? We know the value of mu will be your lateral strain upon longitudinal strain, right? Lateral strain upon longitudinal strain, and we are taking the mode of this magnitude, only magnitude we are discussing, because lateral and longitudinal are of opposite nature, but the value of Poisson ratio will be positive, so we are only taking the magnitude of it. So the Poisson ratio will be equal to your lateral strain upon longitudinal strain. So this is the discussion about your normal strains, which are of 2 types, lateral and longitudinal. Longitudinal means strain in the direction of applied load, and lateral means strain in the direction perpendicular to the applied load. The second type of strain is your volumetric strain, right? The volumetric strain will be equal to your change in volume of the body divided by the original volume, right? Volumetric strain will be change in volume upon your original volume, and volumetric strain is equal to your epsilon x, that is strain in x direction plus strain in y direction plus strain in z direction. This we know, right? The dimensions change in x direction plus the strain in y direction plus the strain in z direction will give you the total change of volume or total volumetric strain, right? We have 3 cases for it. The one is your rectangle cases, if the body is a rectangular shape, or the body may be of cylindrical shape, or the body may be of spherical shape. We will see how the volumetric strain of these are calculated. So I can say, let us first take one, that is rectangular block. The rectangle volume is, if you can say, the rectangle volume, that is V, is length into width into depth. This is the volume of rectangle. If I want to know what is the change of volume, that is dV, so we have to apply the product rule. L, that is, first we'll take BD as a constant into change of length, plus we can say LB as a constant into change of depth, plus your LD as a constant into change of width. Right? We are doing the differentiation using product rule. Now we want to know what is the volumetric strain, that is equal to change of volume upon original volume, that is your BD into DL upon LBD. Total volume is LBD, original volume, plus LB into differentiation of depth. This is not D square, this is differentiation of depth or height, upon LBD, plus LD into differentiation of width upon LBD. Right? So we can cancel BD by BD, LB upon LB, and LD into LD. We will cancel it. So this will be equal to DL upon L plus differentiation of depth upon depth plus differentiation of width upon width. Right? And now what is this? If I can say in this, if length is in x direction, suppose length is in x direction, depth is in d direction, and width is in your z direction, right? If these are the dimensions of this, so change in length upon original length, length is in x direction, so the change in length upon original length is your epsilon x, total strain in x direction. What is the total strain in x direction? Ex lateral because of y, Ex or epsilon x lateral because of Pz, and epsilon x longitudinal because of Px. This combined will be equal to epsilon x, right? What is differentiation of depth or change of depth upon original depth is, this is your depth. The change of depth upon original depth is your strain in y direction, that is equal to your longitudinal strain because of Py plus lateral strain because of Px plus lateral strain because of Pz. So this is epsilon y plus change of width upon original width is, this is your width, that is in z direction. So change of width upon original width is your longitudinal strain because of Pz, lateral strain because of Px plus lateral strain because of Py, and this is your epsilon z. This is your volumetric strain for the rectangle. This is how you can calculate the longitudinal strain of the rectangle. Or sorry, this is the volumetric strain of the rectangle is your strain in x direction, net strain in x direction plus strain in y direction plus strain in z direction. So this is the meaning of your volumetric strain. The next type of the bar or the body will be a cylindrical bar, and we have to find out what is the volumetric strain in case of a cylindrical bar if the body is a cylinder. So we know that in case of a cylindrical bar, the volume of cylinder will be pi by 4 d square L. Right, this is the volume of the cylinder. So if we want to find what is the change of volume, that is dV is equal to pi by 4 is constant into, if I take d square common, then differentiation of length is dl, plus if I take length as a common into differentiation of d square, right, differentiation of d square. So this will be equal to pi by 4 into d square into differentiation of length plus length into differentiation of d square is 2d into differentiation of d, right? 2d plus into differentiation of d. This is your differentiation of d square. So if I want to find what is the volumetric strain, that is change of volume upon original volume, that will be equal to, we have to divide this by pi by 4 d square L. So this will be pi by 4 into d square into differentiation of length plus 2dl into differentiation of d divided by pi by 4 d square L, right? Pi by 4 d square L. So pi by 4 and pi by 4 will cancel out. If you divide these two terms with d square L, this will be change in volume upon original volume is equal to, this is d square cancel out, this is dl upon L plus this is d square L, this is dl, so d and L will cancel out, this will be 2 into differentiation of depth or diameter, differentiation of diameter upon diameter, right? Differentiation of diameter upon diameter, and we will study this in later on, that this is your volumetric strain. In case of pressure vessel, we will see that this will be known as your longitudinal strain plus 2 times of the change of or strain on diameter, that is change of diameter upon original diameter, is known as your hoop stress or circumferential stress or strain. Hoop strain or circumferential strain. We will discuss what is the hoop strain in your pressure vessel chapter. So just now for your understanding, that is the volumetric strain in case of a cylindrical bar is longitudinal strain plus 2 times hoop strain, right? And this hoop strain is also, you can also write it as your longitudinal strain plus 2 times your lateral strain. Hoop strain is also a lateral strain, so this is lateral strain. So this is the diameter, this is the strain in case of a cylindrical bar. The third type of body is your spherical body. So if I can write what is the volume of sphere, the volume of sphere will be 4 by 3 pi r cube, right? The volume of sphere will be 4 by 3 pi r cube, or you can write it as pi d cube upon 6. Pi d cube upon 6. If you want to find what is the change of volume, this is equal to pi by 6 common into differentiation of d cube, right? Differentiation of d cube. So this will be equal to, you can write it as pi by 6, differentiation of d cube is 3d square into differentiation of d, right? Now what is the volumetric strain? Change of volume upon original volume is equal to pi by 6 3d square into differentiation of diameter upon original volume is pi by 6 d cube. So this pi by 6 will cancel out, this d cube and this cube square will be cancelled out. So the volumetric strain will be equal to 3 times change of or differentiation of diameter upon diameter. Differentiation of diameter upon diameter, and this will be the hoop strain. This is hoop strain. So I can write that volumetric strain in case of a sphere will be 3 times your hoop strain. 3 times hoop strain. And we will discuss what is the hoop strain in your pressure vessel chapter. But just now, just remember that in case of sphere, hoop strain will be equal to longitudinal strain. Right, we will discuss this, but just remember that in this case hoop strain will be equal to your circumferential strain, that is change of diameter upon diameter. Right, differentiation of diameter upon diameter. This is your volumetric strain in case of a spherical body. So this is all about your volumetric strain. Right, so we will complete that normal strain. There are two types, lateral and longitudinal, and volumetric strain. Now the third type of, or the second type of strain is your shear strain. The shear strain is because of a shear force. If on any body you applied a shear force, and because of that shear force some strain is developed, that strain is known as the shear strain. Now let us see. We can say that the definition of shear strain is change in initial right angle between two line elements of a body which are parallel to x and y axis respectively. Right. The shear strain definition is the change in the right angle between the two line elements which are parallel to the x and y axis or respectively. We can say, suppose this is a body. If you draw, this is a body. So we can say in this body I am assuming that this is the x-axis, this is your x-axis, and this is your y-axis. We are taking this x and y-axis. This body is a B, C, D, right? This bottom plane is fixed to the ground. This is the cross section. This plane is cross section. BC is a cross section. So if this is the body of length L and width B, that is before loading. Now I applied a load P on this face BC. Just see, we applied a load P here. Right, this is a load P. And now we can say that this load P is, if you write that, if I write here, this load P is which load? A transverse shear load. A transverse shear load. How this member? This is like this. This plane is fixed and I apply a load in this direction, and this load is parallel to cross section, perpendicular to the longitudinal axis and passing through it. So this P will act as a transverse shear load. Right? This will act as a transverse shear load. And the two line elements, I can say this AD is parallel to the x-axis and this AB is parallel to the y-axis. Right? And the initial angle between them is 90 degree. The initial angle between them is 90 degree. If you apply a load in this case, then the bottom plane is, this AD element is fixed. So this body will try to tilt. This body will slightly tilt in this direction. I can say that because of the load P, suppose AB will go to this new position, this body will slightly deform and this B will reach here, that is B dash. If B will slightly incline, then I can say that this C will reach here because of the load P. Right? The C will reach here. C will reach here. Now if I can say that because of this loading, the angle between the AD and AB, which is initially 90 degree, now the angle between these AD and AB dash, final angle will be this. Final angle will be this. So the change of angle is this one. This is the change of angle between the two line elements which are initially perpendicular to each other or parallel to x and y axis, and this angle is known as shear angle, phi. We denote phi is a shear angle. Right. Now if I can say that one thing I can say, we already know from our very good discussion about loads that a transverse shear load is equal to shear force, one shear force which is of constant magnitude, and one varying bending moment. Just remember, this is a concept, very good concept here. You will be very good if you learn this, how to apply the loading, TSL, ETSL, then you will be able to solve any numerical on strength of material. Just stay focused. A transverse shear load will be equal to a shear force and a varying bending moment. And this varying bending moment is maximum at the fixed end. We already see that in our previous discussion if you refer your notes. So I can say, one thing I can say that bending moment, you know already, this bending moment is a normal load. Just remember one thing. It is a normal load. Because of normal load, what happened? Normal stress. Because of normal load, what is there? Which strain is there? Normal strain. Normal strain. Because of bending moment, normal strain must be there because it is a normal load. And because of this shear force, shear strain will be there, right? And we know that this bending moment is maximum at this end. And if I can write this bending moment on BC, this bending moment on BC will be equal to 0, because if you remember that the bending moment will be P into X. X is the distance of a point where you want to calculate the bending moment from the free end. This is a free end, so X is here is 0, so bending moment at this fiber, this BC plane is 0. So if I can say, if the bending moment at BC is 0, so normal stress will be 0, normal strain will be 0. If normal strain is 0, what is the formula of normal strain? That change in dimension upon original dimension. If normal strain is 0, then change in dimension is 0. If change in dimension is 0, then the dimension will remain constant. That means because of shear force, because of this P, that is a shear force on the plane BC only, or on the cross section plane only, shear force is acting. There is no normal force acting on this plane. No normal force means there is no normal stress, there is no normal strain. If normal strain is not there, then the dimension will not change. Only the shape of this body is changing, right? Only the distance, only this body is tilted from this configuration to this configuration, A, B dash, C dash, D. But the length of the top fiber will remain constant. This is the concept here. This length will not change because there is no normal strain. There is no normal strain, so the length of B dash C dash will be same, that is B. The length will not change, right? So I can say that due to shear force, if only shear force is acting, only the shape of a body is changing, not the dimensions. Not the dimensions, because for the dimensions you need a normal strain. But if shear force is there, there is no normal strain, so the change in dimension will be 0. Let us say this is the delta by which this B is displacing, and the distance between B and B dash is delta. Now remember one thing. Now if you can say that, okay, the shear force is there on the plane BC, but there is no normal strain, there is no bending moment on BC. But on each and every plane which is below this BC, at each and every plane there is a bending moment. right? Because of any distance x from this BC, there is a bending moment. And we know bending moment is a normal stress or normal load. And because of normal load, normal strain will come. And because of normal strain, your dimensions will change, right? So I can say that, if you can say from here, if you look about, if you give a look on the diagonal AC, let us assume, let us see what happened to the diagonal AC. This is the initial length of diagonal AC. After this tilting or after the shear strain, the diagonal length of AC will be AC dash. The length of AC will be AC dash, and by just seeing, you can tell that AC dash is more than AC. AC dash is more than AC. So the length of AC will change. The length of the diagonal will change. That means on this plane there must be a normal strain. Then only this dimension is changing. Otherwise this dimension cannot change because of only shear force. So that's why there must be a normal strain in this plane, right? So if you can see that this is a tensile strain. Tensile strain is induced in the AC member. It means there is some normal tensile stress or normal tensile load is acting on this plane. Okay, if I go one step beyond, if you look over the diagonal BD, this is the initial length of diagonal BD. This is the initial length of diagonal BD. So after the tilting, the diagonal length of BD will be B dash D. The diagonal length of BD is B dash D, and by just seeing, you can tell that B dash D length is less than BD. B dash D length is less than BD. The length will decrease. It means dimension changes. It means that there must be a compressive stress or there must be a compressive load, and on the plane of BD there induced compressive strain because of some normal load. So I can write that normal strain on this complete member is not zero, right? Because bending moment is there because of a TSL. So I can say that normal strain on the member is not equal to zero, only the normal strain on the cross section plane is zero, and at any oblique plane other than this BC, there is both normal load and shear load. There is both normal strain and shear strain, right? And we will find out that in our combined stresses and strain chapter, we will find out what is the value of normal strain or normal stress in this direction and normal stress in this direction, right? So that's why I am saying that if a shear force is acting, that doesn't mean in the member there is no normal strain. Normal strain will be there only in case of your plane of cross section. Normal strain will not be there, right? This is the concept of your shear strain, and this is only possible if you remember that how a TSL will work. TSL will give you a shear load and normal load. Because of shear load, shape changes. Because of normal load, dimension changes. Just remember one thing, if in any question there is a concept of dimension change, then just keep one thing in mind, you have to calculate normal strain. And in the question, it is saying that if you can see that only shape is changing and we have to find some angle or anything, then just keep one thing in mind, you have to calculate shear strain, right? So if I can say that if phi is the shear angle, we can say that phi is a shear angle. So the change of initial 90 degree angle, that initial angle is 90 degree, now the angle is this one, the change is phi, so this change is your shear strain. So we can say that shear strain will be equal to shear angle. Now if from the triangle ABB dash, what is the value of tangent phi? Tangent phi is opposite side, that is delta, divided by base, that is length L. So tangent phi is delta upon L. If the angle is small, we know that if the angle is small, then tangent phi will be equal to or approximately equal to phi. So from here you can write that shear angle will be equal to delta upon L. And this is equal to gamma delta upon L. And from the Hooke's law we know that shear strain upon shear stress tau upon shear strain gamma is equal to modulus of rigidity. Is equal to modulus of rigidity, and we will see in our later discussion where this equation is valid. That shear stress upon shear strain is your modulus of rigidity. G is known as modulus of rigidity. Right, it is a elastic constant, and this value is constant for all the materials, depend upon the material. So this is the concept of your shear strain. Right, just remember one thing, shear stress, if any body is subjected to shear force, it doesn't mean that there is no normal strain acting on that body. Only on the cross section normal strain is not there, but on any other plane or any other oblique plane passing through it, there will be a normal strain and your shear strain both. And we will calculate this value in our combined stresses and strains, how to calculate the value of stress and strain on any oblique plane passing through a point which is having an angle theta. We will discuss it.